Hello students. In this session, we are going to discuss about the resonance, which is an important fundamental concept in organic reaction mechanism. Now first we see about the resonance effect. Resonance effect is the polarity produced in a molecule due to interaction between the lone pair of electron and a pi bond. See here in this structure, the lone pair of electron and pi bond. Okay, and see here this the bond is present in between carbon number 1 and 2. That bond is delocalized and it generates the negative charge on the carbon atom, and in the that negative charge is generated here on the carbon number 2. Due to that, carbon number 1 it gets the positive charge, and therefore shifting of a negative charge, it creates again the bond, double bond. This is a pi bond in between carbon number 1 and 2. So this is the delocalization of pi bond, and it is produced due to the interaction between the pi bond between the two adjacent atoms. See the second example in this allyl carbocation resonance form. Okay, and now see here, this is the first structure and the second structure. These two are resonance of each other. And see the third structure, it is a resonance hybrid. Means this negative charge, it is in between the carbon number 1, 2 and 3. It rotates in between all these carbon atoms, and this structure is called as a resonance hybrid structure. Many times the molecule cannot be represented by one structure, or one particular structure does not explain all the observed properties of that molecule. See the example for the benzene, structure of benzene, which is proposed by Kekulé. And according to this, the structure, the bond is between the carbon number 1 and 2. And after that, carbon number 3 and the next 4 carbon atom. So like that, alternate double bond and single bonds are present. According to the Kekulé, this is the structure for the benzene. So these two equivalent structures have been used to represent the benzene, but none of them is truly represent the structure of benzene, or which not explain the properties of benzene. Either of the structure demand the presence of 3 distinct double bond and 3 distinct single bond, and therefore benzene should show 2 type of bond length. Okay, so which 2 bond lengths? One is the single bond length and one is the double bond length. So all the carbon-carbon single bond, they should be close to 1.54 angstrom, and those of the double bond, they should be close to the 1.34 angstrom. However, X-ray crystallography measurements indicate that benzene contain only one type of bond length. Means what is expected? They must show the 2 type of bond length, single bond length and double bond length. But by this X-ray crystallography, what you observe here, they shows only one type of bond length. So all the carbon-carbon bond length in benzene, they are equal, and which is close to 1.39 angstrom. So none of the structure above can correct representation of benzene. Even if we consider that the bond length should be average of the single bond and double bond, so it should be 1.44 angstrom unit. Means what we get here, all the different value, and the correct what you get here, this is 1.39 angstrom. So by this observation, it is observed that both the structure first and second, they demand that the pi electrons are delocalized. The position of this pi bond is fixed here. That is, pi electrons are restricted to C1 and C2 in the first structure, C3 and C4 and C5 and C6. This is about the first structure. Or if we consider here the structure second, the bond is present in carbon number 2 and 3, 4 and 5, and the last one is the 6 and 1. But it is observed that the pi electrons are no longer localized but totally delocalized. That is, all the 6 pi electrons are binding together 6 carbon atoms, and what they make here, all carbon-carbon bond equivalent. And this is represented by the structure third, where all these electrons, these sigma electrons, are completely to be in the delocalization position, these pi electrons. And in the structure third, therefore it should be the more accurate representation of the benzene rather than the Kekulé structure first and second. See what is the first and structure? Just we have studied about the position of the bond, which is a localized. Okay, but that position of this bond is not localized. The electrons, pi electrons are in the delocalization position, and therefore the structure, third structure, it is a resonance hybrid structure. See here, first two, these are the resonance structure, a resonance of each other. There is a delocalization of bond takes place, and due to that they form the resonance hybrid structure. The structure first and second, these are the resonance structure of each other, and the third one is the resonance hybrid structure, which is the actual structure for the benzene, which is the in this structure. See here, all these pi electrons are delocalization, in the delocalized position. Means what you can see here, the continuously these pi electrons are delocalized around this carbon ring. So third structure is called as the resonance hybrid structure, and first and two structures, these are resonance structure of each other. And why this is happened? Due to the delocalization of pi electrons. Here the example for the acetate ion. Acetate ion means from this carboxylate ion CH3 C double bond O OH. From this carboxylate ion, when the it loses one proton, okay, so what it creates, it generates the negative charge on this oxygen, and that means more electron density is on one oxygen, and this negative charge is shared with the another carbon and oxygen bond. And now see in the first structure, the negative charge is delocalized and it forms the double bond in the second structure. Okay, and due to that formation of double bond, the double bond means pi bond which is present on the next carbon and oxygen, it shifted on the head of carbon. It generates the more electron density on the oxygen. Means what we can see here, the delocalization of the electron, they do not belong to the single atom, or nor they are conformed to a bond between the two atoms. Means in this structure, the compound with a delocalized electron is said to have resonance. In the last structure, that electron density is delocalized on this both the oxygen, and therefore this is the resonance hybrid structure. Means what we can say is the neither of these resonance form is correct structure for the carboxylate ion. The actual structure which is composite of the both the two structure is called as the resonance hybrid, and which is drawn by using dotted line to show that electrons are delocalized. And here the resonance forms are shown with a double-headed arrow between them, and this is the last one is the resonance hybrid structure. Okay, which indicates that negative charge means electrons is delocalized over both the oxygen atom, and so that each oxygen atom bears the half of the negative charge, and this delocalization stabilizes the carboxylate ion. These are the important features of resonance. It should be noted that though the resonance forms are different, they only differ in the distribution of the electrons or non-bonding electron. The relative position of all the atoms, that is carbon framework, it remains same. Resonance forms are hypothetical, means molecule never exist in this form, they always exist in the resonance hybrid form, which is the actual form. Resonance is possible due to the delocalization of electrons. Resonance is therefore consequence of delocalization of electron. Resonance leads to stronger bonding, and therefore molecule become more stable. As the number of resonance form increases, the stability of molecule is also increases. Resonance therefore gives additional stability to the molecule, and therefore in the organic reaction mechanism, it's important, these resonance, these are the very important part of the reaction mechanism. This is about the resonance energy, or it is also called as resonance stabilization energy. It is a hypothetical energy of an individual resonance structure. It can be calculated using bond energy values. And the energy of actual molecule is, however, lower than that of any one of the resonance structure. That is, resonance hybrid is more stable than any of the resonance structure. And therefore, the difference in the actual energy and the lowest calculated energy of the resonance structure is called as the resonance energy. And thus, resonance leads to stabilization of the actual molecule. Here, for this example, CO3, the delocalization of electron takes place. It creates a pi bond. Again, the pi bond, delocalization of pi bond takes place. which creates the negative charge on the oxygen. So now see the continuously there is a delocalization of the negative charge where the more electron density and the delocalization of pi electron. So it creates a negative charge on both the oxygen and it forms a resonance hybrid structure. See the second example. For the second example, NO2 group on one oxygen, 3 lone pair of electron, more electron density region on that oxygen. Therefore, the delocalization of this negative charge, delocalization of electron takes place. It creates a negative charge. And due to that, again, the delocalization of pi electron takes place, which creates the more electron density on another oxygen atom. So like that, both the oxygen, they bears the negative charge here. One more example for the O3 oxygen, which having the 3 lone pair of electron having the more electron density region. So due to that, the bond is shifted here, means the delocalization of negative charge, and it creates the positive charge on the another oxygen atom, and the pi bond delocalization of pi bond takes place. So see here the last, this is the first structure here I draw here. This is the for the resonance hybrid structure for the O3, which is the actual structure for the O3, which creates, which or what you can say, which having the on the both oxygens they are partially negatively charged. Now here this is if you consider here the propane. So propane, when one of the base it take one proton from this propane. So what it forms the structure for this propene ion, which creates a negative charge on this carbon, negative charge on CH2. So what it forms the structure CH2 double bond CH2, which having the negative charge. So due to that, the charge is delocalized, negative charge is delocalized on the next carbon atom. And due to that, again, the pi electron, delocalization of pi electron takes place, which creates a negative charge on another carbon atom. Means the delocalization of pi electrons and negative charge takes place. Whereas in the another example, here that when one of the proton is removed from here, it creates a positive charge on this carbon. So as there is a positive charge means less electron density, and due to that the pi bond is delocalized on the next carbon atom, and due to that the another carbon it gets the positively charged, and means these are the less electron density region, and therefore again the shifting of pi bond takes place, which creates a positive charge on another carbon atom. So like that these two are the resonance form of each other. And see the last one is the resonance hybrid structure, which creates on both the this carbon positive charge. Means not only for the formation or generation of the negative charge, for the positive charge also they show the in their resonance structure. So this is a for the resonance hybrid structure, which is the actual structure for this propene ion. There are the two types of this resonance effect, positive resonance effect and negative resonance effect. So positive resonance effect, it is also called as electron donating resonance. Means if one of the substituent group has a lone pair of electron and it donate to the attached pi bond or conjugated system of pi bond, this effect is called as a positive R effect. Always that resonance is happen in the when the system is in the conjugation or what you can say the pi bonds, conjugated system of the pi bond, then only resonance phenomenon takes place. So this is for the positive resonance effect, and it is also called as electron donating resonance. If the substituent group has a tendency to withdraw the electron from the attached pi bond or conjugated system of the pi bond towards itself, is called as the negative resonance effect, or it is also called as electron withdrawing effect. First, we see about the positive resonance effect or electron donating, electron releasing resonance effect. Means when the transfer of electron is away from an atom or a substituent group attached to the conjugated system, it is called as positive resonance effect. This transmission of electron through the chain makes certain positions in the molecule of high electron density, and that explains the reactivity of these positions. See the examples: halogens, hydroxy ion, OR means alkoxy, NH2, NHR, NR2. Okay, then you see this NH3OR or OC double bond OR. So these are the groups. What we can say, these groups are electron donating group or electron releasing inductive effects, as they having the more electrons, and therefore they donate their electron. Release of electron takes place, and they represents positive resonance electron displacement effect. Here example for the positive resonance effect, aniline. In case of aniline, on the nitrogen, lone pair of electron takes place and present, and this lone pair of electron is here shifted on the next position. So it creates double bond in between the nitrogen and carbon. And as the shifting of a lone pair of electron takes place, it forms a double bond, and therefore the next bond, double bond, pi bond, the pi bond is shifted on the head of carbon. It forms a more electron density. Again, as there is a more electron density, it shifted on the next carbon atom, and due to that, the next pi bond is shifted on the head of carbon by generating more electron density at this point. And like that, there's here the continuously delocalization of this pi bond and negative charge. And during this formation of this resonance structure, here for the second structure, it creates a negative charge at ortho position. For the third structure, it creates the negative charge at the para position. And for the fourth, again it creates or generates the negative charge at ortho positions. During this resonance formation, there is a more electron density at only ortho and para position. See one more example for the phenol. On the oxygen, lone pair of electron, and this lone pair of electron delocalized, and they form the double bond in between the oxygen and carbon. Due to that, the next bond, which is pi bonds, it shifted between the next two carbon atom, which creates the negative more electron density, and here it forms a resonance structure by the delocalization of pi electrons. So in this structure also, the more electron density is at ortho and para positions. Due to the positive resonance effect, electron density increases at only ortho and para positions. So these ortho and para positions are electron rich area, more electron density due to the positive resonance effect. Negative resonance effect or electron withdrawing resonance effect. When the transfer of electron is towards the atom or substituent group attached to the conjugated system, they form the negative resonance effect. It is termed as a negative resonance effect, and examples C double bond OH, that is a carboxylic group, aldehyde group, CO, cyanide group, NO2 group. These are the example for the negative resonance effect. See the example, nitrobenzene. In the nitrobenzene, on the nitrogen positive charge. The nitrogen having the positive charge, and therefore the more electron density in the benzene ring, means due to the presence of pi electron, and the nitrogen and oxygen double bond. And see here what happened, the shifting of a pi bond on the head of oxygen, it creates a negative charge on oxygen, and due to that, the bond which is present in between the carbon number 1 and 2, it delocalized in between the carbon and nitrogen, it forms a double bond, means it forms a pi bond. Due to that, at ortho position on the benzene ring, there is a less electron density, means which creates a positive charge on this carbon atom. And here again the delocalization of pi bond takes place, and due to that, in the ortho and para position, see the next structure, it creates a less electron density at para position. The next structure, in the second last structure, it creates a positive charge at ortho position. Means when there is a negative resonance effect takes place or electron withdrawing resonance effect takes place, it creates less electron density at ortho and para positions, or we can say the negative resonance effect in nitrobenzene developed positive polarity at ortho and para position. So this is about the negative resonance effect. And now here what we completed here about the resonance structure. Thank you.